From now on, we will learn numerical integration. In this first lesson, we will be talking about the trapezoidal rule to perform numerical integration. Any function fx, if it has to be integrated, let's say if a function fx dx, that has to be integrated in some limits x0 plus nh, then this can be subdivided into smaller intervals. So this can be written, for example, let's say x0 plus h fx dx, then sum x0 plus h to x0 plus 2h fx dx plus and so on. Let's say x0 plus n minus 1h x0 plus nh fx dx. So this larger integration can be written as the sum of these sub-intervals where we have the data set values given into the table. So such type of integration is known as the numerical integration, for which we have lots of formulas like trapezoidal Simpson's formula, and today we will see how we can derive the trapezoidal formula. For that purpose, we will be using Newton-Cotes quadrature formula. So let's see what is the Newton-Cotes quadrature formula. The Newton-Cotes quadrature formula is for the integration of a function given within an interval. So if this is a lower limit x0 and upper limit xn, then fx dx can be written as, according to the Newton-Cotes quadrature formula, nh within the bracket y0 plus n upon 2 del y0, where this del is the forward difference operator. We had already seen this in the interpolation lessons. So this is del y0. N is the number of intervals and h is the equal interval in the data values. Let's see trapezoidal rule. Here the trapezoidal rule is for n is equal to 1. That means it's for the linear polynomials. When it is for the linear polynomials, that means the higher degree terms will not be considered. So we'll only consider y0, del y0, and the other higher degree terms will be ignored. Let us see if we can write this x0, xn, f of x dx, as I have already written, as the sum of the subintervals, the integration of these subintervals. So if it is x0 and x0 plus h fx dx plus x0 plus h x0 plus 2h fx dx plus and so on x0 plus n minus 1h, and the last one is x0 plus nh fx dx, where we have n intervals. So here number of intervals is n and we have h as the equal distance. So we have h as interval. So now in this equation number 1, that is the Newton-Cotes quadrature formula, let's call it equation number 1. If we substitute n as 1, is for the linear polynomials, so it has to be n is equal to 1. So let's substitute n is equal to 1 in this. On the left hand side we'll have x0 to x1, this is fx dx will be equal to, this n will be equal to 1, this is h y0, n is 1, so this is 1 upon 2 del y0, and we'll ignore the higher terms, higher degree terms, because this is linear polynomial. Now we can solve this a little bit. H y0 plus 1 upon 2, as we know what is the formula for del y0, this is y1 minus y0. So now this is h y0 upon 2, this is 2y0 plus y1 minus y0. We can keep this 2 out. H upon 2. 2y0 minus y0 will be y0 plus y1. So we can see by putting n is equal to 1 in this, the first subinterval comes to be x0 to x1 fx dx, that is h upon 2 y0 plus y1. Similarly, if we take the next subinterval, this will be from x1 to x2 fx dx. So this will be h upon 2, and now we'll increment this. So this will be y1 plus y2. The next subinterval will be from x2 to x3 fx dx, and that will be h upon 2, and this will be y2 plus y3. Similarly, if we write the last term, that is from xn minus 1 till xn fx dx, then this will be h upon 2 yn minus 1 plus yn. Now, just to evaluate this, as we already know that this can be written as the sum of the subinterval integrals. So we'll sum all these, we'll sum this, all these together. And once we'll sum all these, we can see from x0 to x1 we had h upon 2 y0 plus y1. So we have h upon 2, h upon 2, h upon 2 all common. y0 comes once, and then y1 and y1 will come twice. y2, and then in the next y2 will come twice. y3, and in the next y3. So all these terms are coming twice. The first term y0 and the last term yn are only the two terms which are coming once. So this will be rewritten as. So let me write this. So now this is rewritten as x0 to xn fx dx is equal to x0 to x1 fx dx plus x1 to x2 fx dx plus x2 to x3 fx dx plus and so on xn minus 1 xn fx dx. Now just substituting these values, this was h upon 2 y0 plus y1. This was h upon 2 y1 plus y2. This was h upon 2 y2 plus y3 plus and so on, and the last one was h upon 2 yn minus 1 plus yn. Now we can see in all the terms h upon 2 we can take as a common term, and here we can see y0 is coming once, rest y1 coming twice, y2 coming twice, y3 will come twice, and so on. And the last term yn will come once, all will come twice. So we can write it y0 plus yn in one group because they are occurring once, plus twice of all the other terms starting from y1 to yn minus 1. y1 plus y2 plus y3 and so on till yn minus 1. So this is the final trapezoidal formula for n is equal to 1. That means the number of intervals must be multiples of 1. We'll see what this means in the example, and we'll see how we can use this trapezoidal formula to get the integral, to get the numerical integral. So this is the trapezoidal formula. Now let's see with an example how we can find out the numerical integration. Evaluate integral 0 to 6 1 upon 1 plus x square dx by trapezoidal rule. The first decision we need to make is how many intervals we are going to take in this and what will be the interval size, that is the equal interval. So number of intervals has to be the multiple of 1 for the trapezoidal rule. Let's say if we define that we want 5 intervals, so 5 is a multiple of 1. We can also define 7 intervals, again multiple of 1. As we can see, any whole number is a multiple of 1. So we can take any number of intervals in the trapezoidal rule which is a multiple of n is equal to 1. Now from 0 to 6, let's say if we want, let's say if we decide to take h is equal to 1, the interval. So the first value will be 0, then according to h is equal to 1, the next value will be 1. Next is 2, 3, 4, 5 and 6. We could have also taken h as 0.5. Then the first value would have been 0. The second value would have been 0.5. The next value would have been 1. The next value would have been 1.5 and so on. But let's not make so many intervals. So we have taken h is equal to 1 and now we have this as x0, then this will be x1, x2, x3, x4, x5 and for x6. For each this x value, we will find f of fx. So how we can get this f of fx? What is f of x? F of x here is 1 upon 1 plus x square. So for x0, whenever x is 0, we have 1 upon 1 plus 0 square, which is 1. So this is coming 1. Whenever x is 1, so at that time we have 1 upon 1 plus 1 square, that is 1 upon 2 coming 0.5. So we have 0.5. In the same manner, we can calculate all the values of fx for each different x, and these values will be, this is y0 with respect to x0, y1, y2, y3, y4, y5 and finally we have y6. So now this integral from 0 to 6 fx dx can be subdivided into smaller subintervals. 0 to 1 fx dx plus 1 to 2 fx dx plus 2 to 3 fx dx plus 3 to 4 fx dx plus 4 to 5 fx dx, and the last one will be 5 to 6 fx dx. And we can apply the trapezoidal rule on this, where the final value of n here in this case is 6. So we have n is equal to 6 because we have 6 intervals here in this. 0 to 1, interval 1, interval 2, interval 3, 4, 5 and interval number 6. So now let's apply the trapezoidal rule on this for 6 intervals, where 6 is the multiple of 1. So now this will be integral of 0 to 6, 1 upon 1 plus x square dx will be equal to, according to the formula, this is h upon 2. In our case, h is equal to 1. 1 upon 2. Now y0 plus yn. What is y0? 1.0 plus. And what is yn? The last value in this, This is yn 0.027 plus twice of y1. What is y1? 0.5 plus y2. What is y2? 0.2 plus y3 0.1 plus y4 0.0588 plus y5. So let me write here plus 0.385. That's it. We will not take y6 because y6 has already been considered here. Now we need to calculate this. 1.4106. So this is the final answer for the integral 0 to 6 1 upon 1 plus x square dx with the help of trapezoidal rule. In the next lesson, we will talk about the next numerical integration rule, that is Simpson's 1/3 rule.